Hello, welcome back to your physics teacher. Today we're going to be looking at section 1.6 from the Nelson textbook, and in particular we're going to be looking at motion under gravity, which is acceleration due to gravity. Now I want to start off with something that we did before, which is looking at motion with uniform acceleration. So although there were 5 equations that we looked at, I mentioned in my previous video that you only ever need to use 3 of them. So I distinguish them by special symbols. So the first one is the number 1, the star, the fortune telling equation, because it tells us the future, the displacement. The second one is the lightning bolt, which tells you the final velocity of an object. And the third, there's a clock. So this equation doesn't depend on time. Now, the only difference that we're going to be doing today with motion under gravity is that because we are near the surface of the Earth, we're going to take the acceleration. The acceleration is going to be due to gravity. So if you notice the equations, they're almost identical, but instead of A for acceleration, we use the letter G for acceleration due to gravity. Now, the convention that we're going to use is we're going to say G equals to negative G. Now that is a bit confusing, so just bear with me for a moment. The negative is to represent that the vector actually points downwards. And in most of the questions that I do, I always assume that downwards represents the negative direction. So that's why here I have the negative part, which represents the direction, followed by the scalar portion, which is the G without the vector hat, without the top. Or another way to think about it is we approximate near the surface to be approximately 9.8 meters per second square. So if you notice that in all of the equations, instead of acceleration, we use acceleration due to gravity, but this is a vector which points down, and we can approximate to be negative 9.8 meters per second square. So you're going to find that in most problem solving, you only ever need to use these 3 equations. There are 2 others, but I don't ever recall ever having to use them, and I've been teaching physics for about 6 years. So I doubt that you're ever going to use them. So if I never use them and I've been teaching physics and I've graduated already, you probably won't need them. So just stick to these 3. Question number 3. So in this case, we have a baseball. It's thrown straight up into the air. It reaches a maximum height and then falls back down to height from which it was thrown. They're asking us what is the acceleration of the ball. So let's make a quick sketch here. So we have a baseball and it was thrown by someone. And this baseball was thrown and straight up. When they're saying straight up, means that it's not moving sideways while it's going up. It's just going directly upwards. So directly upwards. And then it reaches a maximum height from which it was thrown, and then it falls back down. Now normally you should be putting the dots on top of one another, but to make it clear that it comes up, then it falls down, I put the spacing between a bit. So in this case, that's what it looks like. Now the first part, they're asking us, what is the acceleration of the ball halfway up to its maximum height? Well, if we're considering we're on the planet Earth, and because this motion is happening near the surface of the Earth, then the acceleration during this whole vertical motion is actually due to gravity. So this means that if it's halfway up, it's still on planet Earth near the surface, which we can assume that it still experiences the same amount of acceleration due to gravity, which we call G. So that was kind of a strange question. The acceleration at its maximum height, well again, by the same reasoning, we're still on the planet Earth, and we can still take it to be gravity, which is acceleration due to gravity, g, which is the vector pointing down. And as a number, we approximately take it to be negative 9.8 meters per second square, if you want to be more precise in this case. And C, even halfway back down to the initial height, same reasoning, it's still going to be G. So that question is not so exciting. Just keep in mind that whenever an object is thrown up and is falling back down during the whole vertical motion, it's always experiencing acceleration due to gravity. The only time when the acceleration will be different is while it is still in your hand. So that's why these questions, it assumes the moment that you just released it. All right, we're going to be looking at question number 4. And question number 4 reads, a rubber ball is dropped from a height of 1.5 meters. How long does it take to hit the ground? And what is the velocity of the ball when it has traveled a distance halfway to the ground? So first thing that you should be doing in problem solving is try to visualize the problem. So we have that a rubber ball is dropped. So let's try to draw that situation. Now, whenever objects are being dropped, there's a key interpretation that you could put with numbers. Because whenever you're dropping an object, it means that you're releasing it from rest. In other words, the initial velocity of this object is going to be 0. So this is dropped or released from rest are similar. All right, so whenever you drop an object or they say release from rest, all that tells you is that the initial velocity is going to be 0. Now the other piece of information that we have is that it is dropped from a height of 1.5 meters. Now whenever I put this as representing the length, notice that there's no arrows. It's just the bars to tell you that between those 2 points the length is 1.5 meters. And the question that they're asking us is how long does it take to hit the ground? So we're looking for a time interval. So delta t is unknown, so time to hit the ground. Now in this case we don't have the final velocity, so we're going to leave that as an unknown, so put a question mark as well. And the acceleration, this is where the key part of the lesson actually is. Whenever you're near the surface of the Earth, assume that the acceleration is due to gravity, which we're going to represent by the letter G, and as I mentioned, it's going to be pointing down. Right, so that's never going to be written to you explicitly, so you have to kind of make sense of it because you're on Earth. Now, the other tricky part of this question is because the object's being dropped, that displacement is actually in the downwards direction because we're dealing with vector quantities and we need to consider the directions. So our displacement is actually a vector quantity, and in this case, it points downwards. So our displacement is delta d, which is going to be 1.5 meters down. Our g, we said it was negative 9.8 meters per second square, or you could think of this like 9.8 meters per second square down. They're equivalent. So that's all the information that they give us here. So for part A, what was part A asking us? how long does it take for it to hit the ground? So we're looking for the change in time. So let's look at our equations of motion, and based on what we're given, we're going to try to find out the value. So in this case, we don't have final velocity, so we're going to try to look for an equation that doesn't have final velocity. So you see right away, we start off with the first equation, and right away, that's displacement, initial velocity, time, gravity, and time. So we don't have the final velocity at all in this equation. So it turns out that's the equation we're going to use. Because if you try the second equation, that one is for you to find the final velocity. So that's not good. And the third equation requires for you to also find the final velocity, or for you at least to have been given it. So that's why we're going to use equation 1. Now here comes the really tricky part. It is now a vector equation, and then when you want to write it in the scalar form, you have to consider in what direction the vectors point. Because again, we're taking that convention that when it points down, it's negative, when it points up, it's positive. So our displacement, because it was downwards, we have to write negative 1.5. Our initial velocity started from rest because it was released, so that was 0. And g, we take it to be negative 9.8. Delta t. Or there's a tiny mistake. There should be delta t squared. So let's go back to the equations. Sorry about that. Okay, now it's correct. So all we have to do now, oh wait, another mistake. What's going on? Negative 1 over 2 times 9.8 delta t squared. Now it's correct. Notice that the negative is going to cancel on both sides of the equation. So you're left with 1.5 equals to 1 over 2, 9.8 delta t squared. And now your unknown is the delta t. So what are you going to do? You want to get rid of that coefficient. So the coefficient is 1 over 2 times 9.8. To get rid of the coefficient, divide both sides of the equation by the coefficient, which is 1 over 2 times 9.8. And this is equal to delta t squared. And now for the last step, we have quadratic in time. In other words, delta t squared. To get delta t on its own, we take the square root on both sides. So this will give us that the change in time equals to the square root of 1.5 divided by 1 over 2 times 9.8. So at this point, now we can plug it into our calculator. So this gives us the time interval for it to hit the ground is 0.55 seconds. So that was part A. Now for part B, what was part B asking us? Part B was asking us, what is the velocity of the ball when it has traveled a distance halfway to the ground? So it's the same scenario, but now our displacement is going to be our 1.5 over 2. So if it helps, maybe we could draw another quick picture here. So I could write delta d over 2. So it's half the distance of 1.5, right? Because when it has traveled the distance halfway to the ground, will be our displacement from before divided by 2. And in this case, we're looking for the final velocity. So that's our unknown. Our initial velocity is still 0. Gravity is pointing down. But now we have one more piece of information. We know that the whole time interval to hit the ground was 0.55 seconds. So if you want to be really fancy, for it to reach halfway, you will divide the time by 2. But let's just go with the safe way, because what if you made a mistake with that calculation? So the safe way would be to use an equation that doesn't depend on the time, in case you made a mistake. So remember, there's one equation that doesn't depend on time. So if we look at our formula sheet, that's why I use the clock, to remind myself that, oh, I can use this equation whenever I don't have time. Because I'm looking for the final velocity, and I know my initial velocity is 0, so I can simplify this to v final square equals 2. And remember, g is pointing down, so it's negative 9.8. Our displacement in this case is actually the previous displacement divided by 2. So it'll be 1.5 divided by 2, but since it points down, you still have to put the negative sign. So this will make sense because whenever you have the square root, which we're going to be doing soon, you can't have the square root of a negative number. So that's why the negative 9.8 and the negative 1.5, the negatives are going to cancel out to make the positive. Which is 14.7. And then to isolate for v final, you take the square root on both sides. So square root my answer, which would be 3.8 meters per second. Okay, but that's the scalar part. Because the object was moving down, the velocity, the direction was downwards. Now, this equation is actually the trickiest one of them all. Because notice the left side, it doesn't have a direction associated with it because you're squaring it. But the right side does. So I've never been able to figure out why that is, and it doesn't make sense, but it always works out. So no one's ever given me a right answer. I've asked other teachers, but they haven't answered that. So if you have an answer from your teacher, please let me know. But we do this and it works out. I don't know why. So whenever you go back to state the final answer, though, you have to write v final equals to 3.8 meters per second down. So you have to remember that the object was moving down and velocity points in the direction of motion. So that's why we can write down for this velocity here. All right, that was a lot to take in, so I'm sorry if it's a bit too much for you to handle all at once. But that's why you have in video form, so you can take breaks in between, go back to the parts you need, and please make sure you ask a question if you have any, okay? So now we're going to do question number 5. So an arrow is shot straight up into the air at 80 meters per second. What is the arrow's maximum height? So here an arrow, I'm assuming an archer, and I'm going to use the green arrow from DC. Right, DC is better than Marvel. Okay, so we have an arrow is shot straight up into the air at 80 meters per second. So they're giving you the launching speed. So the initial velocity of this object is 80 meters per second. And because it is getting shot straight up, the initial velocity is pointing up. And whenever an object rises up into the air, the motion that it's going to undergo is going to be slowing down because the acceleration due to gravity is pointing down. So when velocity points up and acceleration points down, this is slowing down. Right? So velocity points up, acceleration points down, this is slowing down. So if it slows down, it stops once it reaches the maximum height, which is why we say that at the maximum height, the object is momentarily at rest. Now that's just a fancy way of saying that it was slowing down until it eventually comes to a stop for that very brief moment in time. So if it stops, the velocity at the top then is going to be 0. All right. So now we got an idea of what this question is modeling. Let's actually go back and read A. What were they asking us to find? What is the arrow's maximum height? All right, so in this case, once again, displacement is the trickiest quantity of them all because you have to consider the direction. So as the object reaches its maximum height, that displacement is going to be a positive value because it's pointing up. So delta D. And this we don't know, so it's our unknown, the question mark. And notice that in this whole question, we don't know how long it took to reach up there. And that gives you a hint. When you don't have time, use the equation that doesn't depend on time. So what was the equation that doesn't depend on time? Well, the one with the clock. And then what you have to do next is consider, all right, are my vectors pointing up? I'm going to put a positive number for it. If it points down, I put a negative number for it. So my velocity at the final, which is the top, it's 0. Initially, it was 80. G points down, so you have to put negative 9.8. My displacement points up, so you put a positive quantity, delta D. So this will make sense. Notice that on both sides, the negative will cancel out. So you get left with 80 squared equals to 2 times 9.8 times delta D. And your target is to isolate for delta D. So that means that you need to divide both sides by the coefficient of delta D, which is 2 times 9.8 on both sides. So our displacement is going to be 80 squared divided by 2 times 9.8. So let's calculate what this is. We get approximately 326 meters. Wow. That might not be correct. We're hoping it is. If it's not, just let me know in the comments, all right? I mean, 80 meters per second is actually quite fast, right? Normally you have questions about 23 meters per second, so 80 is actually really quite fast. It is a superhero after all, right? Anyways, part B is asking us how long does the arrow take to reach its maximum height? So now we're actually looking for time. So we're looking for the time to reach the maximum height. If we look at our equations, since we're looking for time, notice the equation 1 and 2 are both really good candidates to use. And since now you know the maximum height, the distance that it traveled, you could use equation 1 because you have everything else, or equation 2. So the choice is really yours. So you could use either equation 1 or 2 in this case because you have everything else. But notice the equation 2 is a lot easier to handle. It looks more simple, so I'm going to use equation 2. And once again, the tricky part is trying to get the positive sign or the negative sign depending on the direction of the vector. My final velocity at the maximum height is 0. Initially is 80 meters per second up, so it's a positive number. G is a negative number because it points down, negative 9.8. So I can just write my equation now. 0 equals to 80 minus 9.8 times the change in time. Let's isolate for the change in time. So move the 80 to the other side. So it becomes negative. And to isolate for the delta time, I divide by the coefficient of the variable, which is negative 9.8 on both sides. And it's going to work out perfectly because the negatives will cancel out. So see, that's why putting the directions makes a difference. Otherwise, you'll get the wrong answer. So that took place in about 8.2 seconds. And for part C, determine the total amount of time that the arrow's in the air. Determine the total amount of time that the arrow is in the air. This question is not so clear because the archer is launching it up. We don't know the height that the archer is launching it from. So when it goes to the maximum height, we don't know if the archer catches it or if it hits the ground. We don't know how far the person is from the ground. So it's not so clear. But when this happens in physics, you could assume, I'm guessing from the question, that once you launch it up, as it falls back down, that the person caught it from the height from which it was launched. Again, that might have confused you, but the question was confusing to begin with, so that's not me, that's the question. So determine the total amount of time that the arrow is in the air. Well, it's not so clear when we stop letting the arrow be in the air. So if we assume that the arrow is caught from the same height from which it was launched, then we can just use symmetry. We can use the time that it goes up is the same time that it goes down because of the parabolic motion. So just multiply the time that you found by 2, which is 16.4 seconds. Now, if you want to just cover yourself in case the question wasn't clear, you write, it takes 16.4 seconds for it to go up and back down to the launching height. So that way you could argue your marks in this case. Now we're on question number 6. I hope that you're still with me. I know this video is quite long, but if you do need the help, you could just scroll to the question that you need help with, right? So I don't expect you to watch all of it. You should be doing your homework on your own. And this is just if you need a bit more support, so that way you can get help, right? Let me just get some water. Okay, question number 6. A rock is thrown down, so this one is being thrown from the top of a cliff with a velocity of 3.61 meters per second. So let's draw our cliff. Our person, the ball, and it's being, oh, you know what? They're actually assuming that the person is right lying down on top of the cliff. So it must be a mischievous student trying to throw something down at someone. Kind of mean, but what are you going to do? Okay, so a rock is thrown down from the top of the cliff with a velocity of 3.61 meters per second. So there's some initial velocity, but since it's being thrown downwards, the initial velocity points down. And they give us that this cliff has a height of 28.4 meters. They want us to determine the final velocity just before it hits the ground. So this is just before it hits the ground. Alright, but what we do know is that during this whole motion, it's experiencing the acceleration due to gravity. So we do know that the acceleration vector points down, and we can approximate it to be 9.8 meters per second square down. But another thing that occurs is that you have only the height of the cliff, but because you're throwing it down, the displacement vector should also be pointing down. So this is where you're going to make the mistake most likely. So in this case, our displacement is occurring downwards. So our total displacement, if it's just before it's the ground, it's going to be 28.4, which is the height of the cliff, but now it has a direction, so we have to put down. So this is going to make a difference, because remember, if an object points down, not an object, if a vector points down, you put a negative. If it points up, it's positive. We're using that convention. Now notice that it has nothing to do with time. So a very good equation that we're going to probably use is the one that doesn't depend on time. So that's equation 3, right? Remember? So we want to find the final velocity. We have the initial velocity. So here v final square minus 3.61. Notice I put the negative there. You don't have to in this case, in this formula, but I don't want to trick you, so I want to be consistent. So I'm just going to put the negative. G points down, so you have to put negative 9.8. And delta D points down, so you have to put negative 28.4. Now you should try to not put the negative, and you're going to see you're not going to get the right answer. So that simple little negative sign makes a big difference. So we want to isolate for final velocity, so bring the other term to the other side. I guess you can simplify it using a calculator, or you could try to be ambitious and do it all in one step, and to isolate for the final velocity, it would be a big square root. I'll leave that up to you. So I'm going to try to be ambitious, and I'm going to do it all in one step. If I make a mistake, just let me know in the video. Right, I don't have the solution. Okay, this seems pretty reasonable, 23.9 meters per second. That's the magnitude only, but because we know that it was going downwards, so if we want to report the vector quantity, we could write final velocity, 23.9 meters per second, down. Okay, we made it. Hopefully you made it with me, right? Now we're at question number 7. So we want to describe the motion of the object represented by this velocity time graph. Give an example of an object that might undergo this type of motion. Okay, let's see. So we have a velocity time graph. The positive values represent up. The negative will be representing down. So at time 0, we have some initial velocity. Of 30 meters per second. And from this initial velocity, as time moves forward, notice that the velocity values are actually decreasing towards 0. So this means that the object is actually slowing down. But the velocity values were still positive during this section, so it's slowing down while moving in the positive direction. And the next major consideration is what happens here when the velocity is 0. So when the velocity is 0, the object is momentarily at rest, or if it stays at 0, then the object is not moving. So in this case, because the velocity changes afterwards, it's momentarily at rest. But even something even more interesting happened. So the velocity values went from positive to negative. So positive represents going up, negative means falling down. So if we went from positive to negative, where it changed the sign, that's where it changes direction. So momentarily at rest changes direction. And from this velocity 0, notice that as time goes forward, now the velocity values are getting bigger negatively. So the part that's getting bigger means speeding up, and the negatively means that it's speeding up in the negative direction. Now I know it wasn't asked in this case, but I'm just going to plot the position time graph for you. So the position time graph, an object is thrown upwards while slowing down. Once it reaches its maximum height, it's momentarily at rest, so the tangent will be 0. Then it falls back down while speeding up. So that's what it will look like. In this case, we have an object going upwards. then changing direction as it falls down. So there's so many examples, right? The first one that we said, the arrow being shot up because it has some initial velocity, and then it slows down, turns around, falls down while speeding up. So think back to the archer example. Okay, I went kind of quickly in this example because I was a bit tired. So just leave me a comment if you have any questions, all right? And I'll see you in my next video.